Okay, what we're going to try to do here is a fairly typical example, at least early example, of how to go through a substitution. The conclusions we got from our first example, I just want to write down first. So for example, I can see something that says draw the original region, which is what we did. What we did in the first one was we figured out what happened to each of the points of the corners. Now that's fine if you actually have a linear substitution. When you don't have a linear substitution, and this one won't be, we have to figure out what happens to each of the sides. That would have been longer in the first one, but it's actually very short for this one. The next thing we want to do after we know what the new sides are going to be is we draw the new region, and then we use the new region to get the limits of integration, and then we have to take that funny determinant, which we're going to give a name and notation to get the new integral overall. So here we go. We're going to get started. Here's the integral. I want from 0 to 1, 0 to 1 minus x. I've got e to the terrible power to find the integral. And the substitution we're going to use here is x equals u minus uv, y equals uv. Like I say, in Calc 3, you're not going to have to come up with that substitution. There are some books that actually try to get some common sense things, but I'm not even going to worry about that for now. I just want to make the substitution. So step 1 is draw the original region. Well, the original region isn't too bad. Y starts at 0 and goes to 1 minus x, looks like that. And then x only goes as far left as 0 and as far right as 1. And so there's our new region. Now, the next step is to actually figure out what happens to each of the sides. For example, this is y equals 0, this is x equals 0, and this is the line x plus y equals 1. And I guess I'm going to call these A and B. Maybe it's a bad habit to do that, but here we go. I want to know what happens to sides A, B, and C when we make the substitution. So side A becomes what? Well, instead of y equals 0, I get uv equals 0. Now remember, uv can be equals 0 means that u equals 0 or v equals 0. So if I'm going to start over here, over in uv plane, I'm going to put that u of v. If u equals 0, I have the whole v axis. If v equals 0, I have the whole u axis. So that's actually what happens to that one side. It turns into these two sides. Clearly not a linear transformation. What happens to side B? Well, instead of x equals 0, that turns into u minus uv equals 0. I'm going to factor that, so I get u times 1 minus v equals 0. So I'm multiplying those two things together, so either u equals 0 or v equals 1. U equals 0 we already have, that's the v-axis. V equals 1 is just that horizontal line there. And now C, we have this line, the most complicated one, x plus y equals 1. And so I'm going to put u minus uv in for x and uv for y. So this becomes, let's see here, u minus uv plus uv equals 1. So that's x plus y equals 1. The uv's cancel, and I get u equals 1. U equals 1 is just that vertical line there. So we got just a lovely, lovely new region. So the next thing I want to do is start writing down the integral. You can see that the limits of integration here are just going to be 0 to 1 and 0 to 1. It's as nice as I possibly could have. Now, I need to figure out what's going to happen to the integrand. Let's see here. Let's put a little bullet here, see maybe we could do this. The integrand, y over x plus y in the exponent, y is uv. X plus y is u minus uv plus uv. The v's cancel, the v's cancel, and so the new exponent is just v, so I get e to the v, like that. The order is not going to matter because the limits of integration are so nice. That looks like that. And now we have to fill it with that funny looking determinant. So let's go do that funny looking determinant, and let's give it notation. And we'll give it a name. Now the funny determinant that we need to find, and remember the reason we want this is because the areas of the original region got changed when they turned into the areas over here. And this is the actual adjusting factor, making sure that each of the French fries actually has the same volume as the originals. So what we're going to do, we're supposed to find xu, xv, yu, yv, we'll find it first and then we'll give it a name. Xu is just 1 minus v. Xv is minus u. Yu is v. Yv is u. I take that determinant, I get u minus uv plus uv, and that's just u. So that extra little determinant I have to put in right here isn't hard. It's nice and easy. We get an integral that actually is very, very easy to do. Now let's give this determinant some notation. Now we know that, for example, the notation for taking partial derivative is partial something on top, partial something on bottom, but we have this big fraction of things, and what they're going to call that determinant, notation-wise, is we're taking the partials of x and y, right, with respect to u and v, and so that's the notation they're going to give us for that funny determinant, right? Remember, that's not the matrix, that's the actual determinant. The name of this determinant is called the Jacobian determinant. Now, given the example that we just did, it's reasonable that we find it this way. It's reasonable that it fits in right here. After we get comfortable doing 2 or 3 of these, we'll go through the argument about why it actually works this way and not just sort of reason our way through it. Meanwhile, the procedure is fairly straightforward. You draw the original region, you figure what happens to each of the sides, you draw the new region, you find the new limits of integration, you see what happens to the integrand, and then you have to insert that extra determinant in there to make sure that the volume didn't actually change when we made that substitution.